Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Okay, so good morning, everyone. So my name is Peter Druschel, and I'd like to first of all thank the organizers very much for inviting me to be here in Bangalore. It's a great pleasure and also a great honor to be able to speak to you here this week among such a set of eminent scholars and speakers. So what I'll be doing is for the next 5 hours actually is to tell you a little bit about decentralized distributed systems, in some contexts also called peer-to-peer systems, and in particular a technology called distributed hash tables, which was invented in that context, and its various different facets, and in particular also, what it can do and cannot do. So some credits are due to begin with. The part of the work that's been done in my group would not have been possible without the contributions of my group members who have all turned into former group members by now, and many colleagues, as you can see, at various institutions throughout the world, including Microsoft Research. And I should also acknowledge the funding that we've received over the years, and again, including from Microsoft Research. So what we'll try to do in this course is to talk to you a little bit about peer-to-peer systems, and in particular, distributed hash tables, which is a technology that has actually received a tremendous amount of attention over the last decade or so. And some of these systems, or at least systems based on that technology, are now in production use, although as we'll see, the applications in which it's actually used are not exactly the ones for which the technology was originally actually conceived. And that's in itself an interesting question why that is, and we'll use that to try to understand what the technology can actually do and what it can perhaps not do. So we'll focus on those mostly in the first part of the lecture on the technology, and then in the second part of the lecture tomorrow, take a bit more of a perspective, a retrospective of what we've learned from using and studying this technology. So like I mentioned, this work actually started around 2001, at least in the academic community, although it was sparked by some earlier inventions that were not done in the research community, but more among open software and peer-to-peer interested people and other innovators who came up with ideas like Napster, which you may or may not remember. It was a music sharing system that was subsequently shut down because of copyright issues. A very innovative system called Freenet, where people tried to have an open, decentralized system for anonymous storage and sharing of information. And by the introduction of SETI at Home, which is a very interesting system in which people can contribute computing resources towards a scientific problem. And there are today many examples of these kinds of participatory scientific computing projects. So that actually really sparked and inspired the research community to take a closer look at that technology. And what happened then is, what some people term as the technology hype cycle. There was a huge spark and uprise in activity in the research community and beyond. And people were very excited about what all we thought we could do with this technology. And then at some point it reached a point where people started to realize that some of these things that we thought would be possible are actually very, very, very hard in a completely decentralized manner. And that sort of caused a reversal in the mood, and people started to get rather pessimistic, readjusting expectations, and many people in fact lost interest and moved on to other problems. And now we have a bit of an upswing where there's a better understanding of what the various technology that was invented can actually do and cannot do, and you start to see it in industrial use. And this is quite typical of technology sometimes. So I'm not sure we're now, approaching this plateau of productivity as it is termed here, but like I said, the technology is being used in places, and so it's a good time to perhaps look at this technology and also take a bit of a retrospective. I'm not sure we're at the stage of enlightenment. I certainly don't have any to offer to you, but perhaps a little bit of useful information throughout this course. Okay, so in terms of outline, today we'll mostly be talking about what is an overlay network. We'll introduce some basic techniques such as consistent hashing and key-based routing. We'll see how to use that to build a decentralized system that can actually store and share state, and then how we can use the same basic primitives to implement some forms of scalable group communication. In tomorrow's lecture, we'll then focus more on some of the advanced challenges, like what happens when you're trying to actually get strong consistency in such a system, what happens when you're trying to tolerate malicious participants or massive failures. And then we'll look at some real applications today that use the technology, and we'll take a bit of a retrospective. And then, in the third part of the lecture, actually on Friday, I'll talk about a little bit more recent work on accountability in distributed systems, which is relevant to these kinds of decentralized systems, but also to other kinds of systems. Okay, as before, please ask questions at any time. So what's a decentralized system? So in general, we call a decentralized system a distributed system where the components, meaning principally the participating computers or devices, are symmetric, more or less, which means they're in principle able to take on any of the relevant tasks in the system. Okay? So there's no a priori distinction between nodes that have certain hardware capabilities or large capacity that predestines them for a particular role in the system. And moreover, both the control of the system and the state of the system is more or less decentralized. Okay? And the third important aspect of these kinds of systems is that they're self-organizing. What I mean by that is that you should be able to, when you're trying to expand the system, just unpack another computer or device, okay, attach it to the network, perhaps provide it with an identity and some key materials so it can authenticate itself to the system. And from that point on, the software should itself integrate that node and figure out how to use its resources in the most effective way. Okay? So there's no manual configuration that says, this node shall store that information, run these functions, play that role in the system. Right? That should all happen automatically. So why are people interested in these systems? And in fact, people have been interested in these kinds of systems going back to the at least 70s. Although interest has, peaked. There was a lot of early interest, then, interest sort of waned a little bit, and people were more interested in client-server type systems, which are inherently asymmetric. And then again, about 10 years ago, there was this renewed interest in these kinds of fully, or more or less fully decentralized systems. So why are people interested in them? Well, they promise certain interesting features or aspects. Right? First of all, what I term here as organic growth or elasticity. Okay? So we call this property typically organic growth when we're talking about peer-to-peer systems. So a peer-to-peer system is just a decentralized system where the model is that individuals contribute their own resources. Right? You as an individual can join this decentralized system by contributing maybe your machine or some part of the resources of your machine, and in return you're expecting access to the service, the capability that this decentralized system is providing. Okay? That's the model. It's sort of a cooperative participatory model. Whereas you can also imagine decentralized systems which are infrastructure-based, meaning somebody actually buys a bunch of hardware, puts them perhaps into a data center, and that hardware is dedicated to serve the purpose, whatever this kind of system is providing. When we talk about peer-to-peer system, we call this property organic growth because it sort of, the idea is as more users are interested in joining the system, they contribute resources, but they also impose additional load onto the system. And ideally, the system should be able to just handle that additional load with the resources that the user, him or herself, has provided. Okay? So there's this nice balance or organic growth. Or if you're talking about infrastructure-based decentralized system, the idea is that I can just, if I need more capacity, I add more computers, I dedicate more resources in my data center, and then the property is called elasticity, but it's basically the same underlying concept. Or as Chandu said yesterday, I believe, we used to call it incremental scalability. It's all the same concept. The other interesting property that these decentralized systems promise is a certain resilience to faults, because the symmetric nature of these systems and the ability to, for one computer to take over the role of others, in principle should enable it to tolerate failures more or less easily. Okay? If one computer fails, another takes over. In fact, you could even imagine that such a system might be more resilient to certain types of security attacks, because if you think about it, it's more difficult for an attacker to actually target the system if the nodes are all symmetric and anyone can play any role. If you compare that with a centralized system in which you know that if I go after this particular critical infrastructure node, right, and I manage to compromise it, the whole system will go offline. Now, all of these are promises, right? Whether we can actually turn them into reality is another matter, and we'll have to talk about that. Again, if you're talking about the peer-to-peer world, this model of participatory computing, then these systems have this ability to deploy a new system without much upfront investment. Essentially, what you have to do is develop the software, maybe put up one or two nodes of your own from your own resources, put it out there and see if people like it. Right? If people like it, they will join with their own resources, thereby contributing the needed additional resources to cover, to expand the system. So the barrier for deployment is very low if you compare it to, for instance, a situation where you would have to put up a data center, before you can start providing the service. And secondly, again, and this is applicable in this world of peer-to-peer systems, if you do have a system that lots of people want to join because they offer something that people want to contribute to, you may very well have access to a huge abundance of resources, which is in itself an interesting capability. And moreover, if those resources are actually contributed in different countries, in very different physical locations, perhaps with different network attachments, that gives you a certain diversity of resources, which is in itself a source of strength, right? Because often systems that have diversity, different network attachments, different physical locations, are more robust to certain failures or even attacks than a system that has all the resources, homogeneous in a certain sense. Okay, so of course we're talking here about a system at a very, very high level, right? At this level of abstraction, all I'm showing you is a set of computers and a network. Whether we can actually turn these promises, these potentials into reality will depend on many other parts of the system, and this is what we're going to have to study. So where are these systems deployed? Well, there's a number of different environments. One is in so-called overlay networks. An overlay network is basically a logical network that connects a set of internet-attached devices. Okay? They form their own logical network on top of the internet. And this is what typically happens with peer-to-peer systems or with federated or decentralized systems that provide some other kind of internet service. You can also deploy them in data centers where the individual participating nodes are simply the individual server blades or servers in the rack. And also another deployment environment are things like ad hoc wireless sensor networks or delay-tolerant networks, okay, where the devices that participate are typically mobile wireless devices or those with intermittent connectivity to the internet. So why are those interesting employment scenarios? Because they're all highly dynamic networks. Okay? If you think about it, in all those networks, nodes tend to come and go. It's perhaps least obvious in a data center, but if you realize that data centers are very, very large, they have thousands or 10,000s of servers, failures are very common. Okay? That makes these networks also very dynamic. In an overlay network, the dynamic property comes from the fact that people may join and leave at different times. Okay? And of course, that the internet is not always available, particularly on on the fringes, where your home network may go offline at certain times. Okay, so in this lecture, initially we'll focus mostly on overlay networks, and then later on we'll consider, to some extent, data centers. So what is an overlay network? Well, like I said, here you're interested in a set of devices connected to the internet. I was rather unimaginative here in my illustration by having things that look like desktop computers, but of course they could be any kinds of devices. They could be servers in the data center, they could be notebooks, they could even be mobile devices. Although you'd have to be careful because mobile devices would introduce a lot of dynamic behavior because they're always moving and they're always going offline and online. So once you have these set of internet connected devices, you in software can connect them or organize them in a so-called overlay network, which you can think of just a set of logical edges that connect those devices. Okay? They're just logical edges because there are no physical network connections per se associated with those, because you're relying on the underlying physical internet to provide the actual connectivity. So what it means to have an edge in this overlay network simply means that the two devices that are connected by that edge know of each other's IP address. They're aware of each other. Okay? That's all it means. And now there's a question, what sort of topology do you want to adopt? How strong should the connectivity be? What sort of graph structure should emerge? And again, there's different approaches. There are some overlays that are called structured. So that means the overlay structure actually conforms to a specific graph structure, which gives the overlay network certain properties. And we'll learn about that. Or they could be unstructured, which means that actually the topology that emerges is a function of certain non-deterministic processes, such as the order in which certain devices are joining, or which nodes they choose to attach to early on when they first join. Okay? And again, we'll go back to that. So at this point, we have this overlay network, which is just a bunch of computers that are logically connected to each other in certain pairs. They form a network. Now you could start to do things with that, right? You could start to implement services, but if we want to have interesting services, we're going to have to start talking about how to maintain state in such a system. Okay? Because if you think about it, the sorts of things that you can do without state are rather limited. You can implement a service that basically provides a pure function, okay? Such as a service that converts Word documents into PDF documents. It has no side effects, right? You ship it a document, you get back a document, it remembers nothing about your job. That's interesting, but the scope of applications of that sort is rather limited. In fact, if you think about this document conversion thing, the minute you want to have a per-user profile that allows you to attach some preferences to a user, so you don't have to, conversion preferences that you want to use every time you do a conversion, you need to start maintaining some per-user state. If you want to do billing, if you want to have quotas, anything of that sort, you need to have state. Point is, right, we can't do much if we don't have state. Okay, so let's add state. Let's consider the state as consisting of a set of state objects. And those objects can be of different color, meaning they contain different information, have different purposes. And we're going to have to store them somewhere in that system, on some of the computers, because that's the only storage we have. Now, the problem, of course, is that in this decentralized systems, nodes can come and go. Right? We have a symmetric system in which there is not upfront any dedicated piece of hardware that's always going to be there. Whereas this set of state objects, we really want that to remain. Okay? For state to make sense, it has to always be there regardless of the set of computers that are currently participating. Okay, so that means we need to dynamically replicate state, by which I mean we need to look which computers are currently available and then somehow assign the set of state objects to these participating computers in some sensible way to perhaps balance load. And in order to not lose any of these state objects just because one computer fails or departs abruptly, we better replicate those state objects. Okay? Store any given state object on multiple computers, which is you see here that certain colors appear on multiple computers. So that, of course, raises the question of how do we do that? Now, at this point, let's distinguish between, first of all, what I would call a partly decentralized system. So a partly decentralized system architecturally is still a decentralized system, meaning any of the computers can play in principle any role, but in practice what we do is we at any given time have a particular node that plays the role of a controller node. Okay? And this decision who is the controller node can be dynamic. We can do, for instance, something like leader election. Right? There are algorithms by which a group of nodes can simply do an election, and then what emerges is one computer that everyone knows plays that controller role. And this controller role can now maintain an index of which computer has what state object stored. Okay? It's a centralized index. It says this computer has a copy of the green object, and this other computer also has a copy of the green object. And now this controller node can basically mediate and control and coordinate access to those state objects. It can also keep track that all objects are sufficiently replicated, and when one node goes offline or a new node comes, that controller can do the appropriate actions. Okay? And so as a result of this, if you think about it, having a simple node-to-node communication service is perfectly adequate, because in principle, all the nodes need to be able to do at the level of the communications network, the overlay network, is to be able to know who is the controller node and to be able to send a message to that controller node, because that will enable it to find out where all the state objects are. And once it knows that, it can contact those nodes to access the state. Similarly, when a node wants to update an object, it basically updates the object and lets the controller node know that there's now a new version of this object somewhere in the system. Now let's go to a fully decentralized system. So in a fully decentralized system, oh, by the way, this approach of what I call here a partly decentralized system with this controller node is quite common, right? In many applications, that's a very smart thing to do. If you're worried about fault tolerance, meaning what happens if that controller fails, in many applications that's something that can be handled. So for instance, a very simple approach would be if the controller fails, let's just have another election, elect a new controller node. Now, of course, that new controller node needs to know where everything is. How does it find that out? Any ideas? Sorry? Right. So in some sense, right, you can just broadcast to all the nodes and ask them, what do you have? Right? And you can assemble all the information that the controller node needs. So at this point, a failing controller node just causes a temporary loss of availability and performance, because we need to have some time to elect a new controller node and have it gather all the relevant information. By the way, if you want to do better than that, you can also replicate the controller node using a technique like replicated state machines, which is something we'll hear also this week about. Right? So you can have a number of controller nodes that actually jointly act as a single controller node. Now the failure of one of those will not immediately cause the controller node to go offline. Nevertheless, right, there are situations in which you want to neither have a single controller node or a replicated controller node, perhaps for scalability reasons, or because in a peer-to-peer system, there's actually not clear who should play that role. Right? Who would want to volunteer to say my node, should play the controller node, because that controller node, of course, is going to have more work to do. Right? It'll have a higher CPU load, may need more memory. It'll certainly need more network bandwidth because it has to receive a lot of traffic, coordinating actions. Okay, so for all these reasons, people are also interested in completely decentralized systems in which there is no dedicated controller node, not even a dynamically elected one. Now, it turns out in such a node, there's obviously the question, how do I, if I want to access a state object, how do I find out where to go, right? Where are the replicas of a particular state object? And this is a problem because, in some sense, here I'm not interested in contacting particular nodes, which is what a typical overlay communication system is going to give me, right? It gives me an IP address by which I can access any of those participating nodes. But that's not really the question I want to ask. What I want to ask is, how do I contact a particular state object? And I couldn't care less in principle, right, where that state object is stored and who currently maintains it. So I'd like to be able to communicate in a way that allows me to address state objects, not individual nodes. And then to do that, the overlay network needs to have a communication service that maintains in its implementation a kind of index, okay, that knows where the state objects are, so that when someone asks to access a particular object, it'll automatically contact the appropriate nodes. Okay? So this has led to the idea of a so-called distributed hash table. So a distributed hash table is the same sort of basic, has the same semantics as a conventional hash table. You can think of it as a shared set of tuples consisting of a key and a value. Okay? And the basic API that you typically use is also the one that you expect from a hash table. You have an insert operation with the key and the value, and there's a lookup operation which takes a key and returns you the current value associated with that key. Okay? So you see the connection. I now have a way of addressing such objects. The color of my state objects are represented by the key value. And now I can ask for a key, and it'll just give me the associated value. And I don't have to worry about where those values are stored and who replicates them at the moment. So the question is, though, how do we, normally hash tables are an in-memory data structure that's maintained on one computer. Right? But we want it to actually be distributed among a set of decentralized nodes in such a way that the load is balanced, and in such a way that the failure of any node does not cause the current tuple to be lost. So to do that, we have to somehow dynamically partition the set of tuples that exist in the system among the participating nodes, okay? Among the set of currently participating nodes. And keep in mind, they come and go all the time. And of course, we have to replicate them for fault tolerance, because we don't want to lose any one tuple just because a computer fails. Okay. And then once we have that, once we have a way of, in a decentralized manner, decide which node should store a copy of which tuple, we need to have a way of being able to access that tuple, right? Implement that insert and lookup operation. And that's done with a technique called key-based overlay routing. Yes?
Dynamic partitioning here means that mapping from keys to a set of nodes is not fixed.
That's right. Actually, do we have a microphone? That's probably going to be easier if you ask questions. So I'll repeat the question. The question was, is the dynamic partitioning of tuples to participating nodes dynamic? Does it change over time? And the answer is yes. In fact, it has to, right? Because remember, the set of participating computers changes over time. Some nodes fail or they depart, others join, right? So we need to definitely change that partitioning to adjust for that. The mapping from, so it depends a little bit on what you mean by partition. So let me defer that question and let's look at how it's actually done, and then see if your question is still relevant. Okay, so let's look at this first part of the problem, right? How do we dynamically partition the tuples? So there's a very clever technique that people have invented. David Karger is credited, and his colleagues in '97 for this. It's called consistent hashing. It's one of those ideas that has come out of this general line of work that's really, really clever and really good. And you'll hear me say that over the course of this lecture several times. All the really important ideas in systems are simple. Okay. There's some reason for that, because typically, by the way you implement a simple idea and you deal with all the various complications of failures and other things that arise in a distributed system, is going to be sufficiently complicated anyway. Anyway, let's look at this technique. Right. So first of all, what we have here is a circular identifier space. So think of that as the set of keys that exist in the system or in the tuple space, right? That hash table. And let's assume that it's actually the set of integers that you can represent with a 160-bit value. Okay? And we'll make it circular by wrapping it around. So when you reach 2 to the 160 minus 1, the next value goes back to 0. Right? So it's a wrapped space. And it's very, very large. And now what we do, first of all, is we assign an identifier, a unique identifier, to each participating node in the system. Okay? And we'll call that a node ID. They're shown in blue here. So if we assign those values in such a way that they're uniform, randomly distributed around that key space, we're going to see a picture like that where these blue node IDs appear in that circular key space, sort of more or less evenly. How can we do that? How can we assign identifiers in such a way that they nicely distribute this way? Well, any ideas? Remember, we don't want to have a centralized controller node that says, let me see what node IDs I have, and when a new one is needed, let me pick the right one to give a nice even distribution. We don't have that. We want to do it in a decentralized manner. Randomly choose one, exactly. So for instance, and the other thing, of course, keep in mind, you want to make sure that those node IDs are unique, okay, with very high probability. So a simple thing you can do is just take some quantity that you know is unique to your device, such as its IP address, or if your IP address assignment is dynamic, take the MAC address. Okay? The MAC address is definitely going to be unique. And apply to it a hash function, like SHA-1 or SHA-256. Right? So with very high probability, that's going to give you a unique hash value. And the set of hash values that are going to result from hashing many different MACs is going to be uniformly distributed in that space. Okay? And notice you can do that without coordination. Right? Every node can just hash its MAC address. It knows what its node ID is. Okay, so now we're going to do the same thing with keys. Right? Remember, keys signify state objects. So let's take some unique name for a particular state object. Okay? For instance, one way to do that is to say, let's just hash its content. Okay? If the content of an object is actually uniquely identifies the object, then this is going to give you a unique identifier. And you can use that as the key and also map it into that same circular space. Okay? So if you have many data objects, they all get keys assigned, and they're also approximately randomly and uniformly distributed around that circular space. Okay? And so now what we do, and this is what's called consistent hashing, we simply say that the node currently responsible for storing an object is the one that is numerically very close, arithmetically very close, or the closest to a given key. Okay? So in our example here, this key here is closest to this particular node, simply because their node identifiers are similar. Okay? So this is a completely random, arbitrary assignment, but nevertheless, it gives you a simple way of deciding which node should store which key. Okay? And the other nice thing is that if you make sure that the node IDs and the keys are uniformly distributed in that space, you're going to get a fairly even distribution of the number of keys, or tuples, if you will, to an individual node. So you get some rough load balancing. It's not perfect statistically, but you can actually make it better by playing some tricks that are straightforward, but I'm not going to talk about them now to not confuse issues. And this is good enough for most purposes. Okay. So we now have a completely decentralized way of deciding which node should store which object. Okay. I haven't told you yet how we do replication. Let's ignore replication for a moment. Let's just assume we're going to store one copy of each object. Okay? And we'll extend that later. So the other nice, very, very nice property about this way of assigning keys to node IDs is the following. When a new node comes in, right? So you saw that little node here fly in from the right. So this node has just appeared in our key space. It was a node added to the system. Of course, that means we need to adjust our partitioning because we want to also store some objects onto that new node. Okay? Now, if you think about it, if you used any conventional hashing scheme, adding a node or removing a node would change the number of buckets, right? The number of hash buckets. So that would mean that virtually all keys and all assignments of keys to buckets in the entire system would change. That would be a problem, right? If you had a large system, and just because one node joined, you now need to rehash all the keys, and that all the objects would have to move to different nodes. Right? That would clearly not scale. in this consistent hashing scheme, if you see, all that happens is that keys in this range here, okay? So let me make the node go away again. Previously, if we're going to decide, on a key should go to the node that's arithmetically closest, then basically anything in this segment of the ring and this segment of the ring will go to that node, right? Basically sort of the halfway points between a node and its neighbor, and the halfway point here, anything from here, this halfway point to this halfway point goes to this node. If a new node shows up, it's only keys in this range and in this range, from this halfway point to this halfway point, that are going to have to be moved from the neighbors, from this one to this node and from this one to this node. So in fact, if you think about it, only an expected k over n keys, so number of keys divided by number of nodes, will have to change their assignment, right? Only a local redistribution of keys is necessary. That's what makes this technique useful. Okay. All right. So now we know how to assign tuples to nodes in a dynamic fashion, right? Depending on the current membership, depending on the current set of participating computers. Of course, one thing we have lost, and you have to realize this, we've given up the flexibility to decide which object should be stored on which node. Okay? So if perhaps there are some additional constraints where you would like to have certain objects to be stored on particular nodes because you know that node frequently needs access to that state object, you cannot easily do that. Okay? That's something we had to give up. There's no free lunch. We'll talk later about how we can recover this loss to some extent. Yes? Can you use the microphone, please?
Yeah, redistributing keys from nearby nodes won't ensure uniform distribution among all the other nodes?
So remember that it's still the case that each node is responsible for about k over n of the key space. Okay. Okay. So as long as you have a uniform distribution of node identifiers in this key space, and you have a uniform distribution of keys around the key space, this assignment should still give you, not quite actually, if you look at the statistics, a uniform distribution of number of keys to objects, but it's not too far off. Okay. Okay, so the next thing we need to do, of course, is we've assigned these state objects to nodes. We need to have a way of accessing them. And this is done with what's called a key-based routing primitive. So every overlay node implements this primitive that routes a message M to the live participating node that is currently responsible for the key X. Okay? And we know who's responsible for that key based on this consistent hashing scheme, which everyone can compute. Now, it turns out that this key-based routing primitive also does something else, namely, as it routes the message through the overlay network, it performs upcalls at the intermediate nodes, giving applications an opportunity to do certain computations or even redirect the route. But this is something I will just mention in passing at this point. We'll talk about it more later. Okay? Yes? Yes? Precisely, yes. So if this node, let's make this node fly away again here, right? This one, its keys are now going to be, its keys used to be roughly in this range. They're going to be divided among this node and this node, which are going to take over. That's something we'll get to, right? Obviously, there has to be some sort of a fault detection mechanism that says, oh, my neighbor has died. I better do something. Okay? We'll get to that. Yes? Do we have the microphone?
When that node dies, so obviously the keys that are in that node are not available. So how do you?
Yes, very good question. Remember when I said I'm not going to talk about replication at this stage, not to confuse issues.
Okay,
that's why
right.
I didn't talk about failures.
Okay.
So what in practice you will have to do is we'll have to make sure that more than one copy of each tuple exists, right, of each key, so that when a node fails, the neighboring nodes, which are now taking over the responsibility for those keys, they know where to fetch that value. Okay.
Okay. All
So
right.
hang on to that thought.
Okay.
Okay. Or I can quickly tell you, just as a preview, what we're actually going to do is we're going to not only store a tuple on the node that is closest to the key, but we're going to store it on some number of nodes that are the closest to the key. Okay? So that maybe a key is not only stored on this node, but also on this node and maybe also on this node. Okay? So that when one goes away, other neighbors still have a value.
Okay.
Okay. Right. So how do we implement this key-based routing primitive? Remember, this is supposed to take a message, you give it a key, and it automatically sends it to the appropriate node that is responsible for that key. Okay? So one thing we could, of course, do is to say every node should maintain a table that maps ranges of keys to the associated node that is responsible for that key, including an IP address of that node. Okay? So now when someone calls KBR message key, you simply take that key, you look it up in your table, in which range it falls. And remember, each node is responsible for a contiguous range of keys. You look up the IP address of the associated node, and you simply route the message to that node. Okay? End of story. In one hop, you have gone to the appropriate node, and applications don't have to worry about which node it is. They don't care. So, in fact, you can implement that. It's called a one-hop key-based routing, or the associated DHTs are called sometimes one-hop DHTs. The only limitation is that if you think about it, as the system grows, that table will grow. Okay? If you have a very large system with many nodes, every node needs to store a table with all the key ranges and the associated nodes. So that table is going to grow linearly with the size of the network. That may or may not be a problem, but keep in mind that this is not only a question of storage scalability, right? Because you also need to make sure that that table is kept up to date. As nodes come and go, you need to make sure that you update the tables of all the other nodes, right? So that they know that the key ranges now have been shifted. Okay? This is the real problem in practice, and this is actually quite common in the design of such systems, that you're less concerned about space than you are about keeping that state up to date, right? Because that causes, that requires network traffic. So if you think about it, the problem is that that you have a problem whenever you have either a very high node count or very high churn, means a very high rate of departure or arrival. Okay? The more the higher the rate of membership change, the higher the absolute numbers of members, the more of a problem you have, because your network traffic required to update all the tables is going to increase with that. Okay. So this is the reason why in general, right, you have to do better than store a complete routing table. And of course, as you might suspect, there are ways to do this, to get by with a much smaller per node routing table. Of course, again, there's no free lunch. We're going to have to pay something. And what we pay in this case is that we have to give up the ability to route to any particular key in one hop. Okay? We'll have to go through multiple overlay nodes. Okay, so here's a particular scheme, key-based routing scheme that's called prefix-based. There are others. But for concreteness, let me describe this particular one. What you do here is that let's first look how the routing works. So this particular node down here, receives a call from an application that this message M should be routed towards this particular key. Okay? And this is written in hexadecimal. So each digit is a 4-bit value, okay? Ranging from 0 to F. So, and the node that receives this call, it has the node ID 65A1FC. So what it does is it says, well, I don't have a complete routing table, so I do not know which node is responsible for this particular key. Okay? But let me route it to a node whose node ID starts with a D. Okay? So with a node whose node identifier starts with a digit that matches the digit in the requested key. Okay? And this node again forwards the message to a node that matches the key, whose node ID matches the key in 2 digits. Okay? And so on until we reach this node, which matches, whose node ID matches the key in 3 digits. Now, depending on the size of the network, we may have to take additional routes, but at some point, we're going to reach a node such that no nodes exists that has a longer prefix match with the requested key. Okay? So in this particular case, it looks like we don't, we're not quite sure where the midway point is. It's either the case that, in fact, this node is responsible for the key, or its immediate neighbor is responsible for the key. Okay? And because nodes know their immediate neighbors, they can decide. At that point, they know exactly who's responsible. So it's possible that, and if you also assume that there's, in fact, another node here in between, which has the same prefix match, but is closer to the key, you may, again, have to forward it one more hop to get here. Okay? So you can see sort of from this progression, because we're basically matching one digit at a time and thereby cutting the number of candidate nodes that could be responsible for the key by a factor of 16 every time. Okay, we route one hop. You can sort of see that we're expecting here a logarithmic number of routing steps. In fact, it's the expected number is almost precisely log base 16 of n. Okay? So this is it's not direct hop, but it's a very fast progression. Meaning, even in a system with tens of or hundred thousands of nodes, you would only have a small, handful of routing hops. Yes?
Why is the hop or prefix match restricted to 1 digit at a time? Why are we not trying to
Okay. Very good question. That has to do with the size of the routing tables, and I think it'll become clear on the next slide when I show you what routing state each node is actually storing. Okay? Because remember, in the limit, what you're asking me is, why don't I not directly route to the correct node? Just take the longest prefix match in the system, but that of course would require the full routing table, and I want to have a much smaller one. Okay? It'll also turn out that if we use this routing technique, then we get by with a routing table that's only logarithmic in the size of the network. Okay? So there's a log-log trade-off here. It turns out this is not, and I'll show you why that is. Let me just note also, this is not optimal. You can actually develop such routing techniques that give you a logarithmic number of routing hops and a constant size routing table. It's just that the protocols are hideously complicated. So in practice, people have not implemented that. Okay, so now let's look at the routing table that each node has to store to be able to route messages in this particular way. Okay. So let's look at, you see that the routing table has different levels, right? It's a table which matches a particular, basically maps a particular node identifier of a particular node to an associated IP address, right? That's basically what we need to know. What is the node ID of a node? What is its associated IP address, so we can route to it. So at the top level of this routing table, we basically have one node for each of the possible values of the leading digit of the node ID. Okay? So here is some node whose node ID starts with a 0, and X means I don't care, right? I don't know I don't care what the suffix is. An arbitrary value could follow. The important thing is that I need to have I need to know a node with all the possible values of the first digit of the node ID, except my own, right? This is the node whose own node ID starts with a 6, so I don't need a neighbor with a 6 because I myself am a 6, okay? So what does this allow me to do? Well, given any key-based routing invocation, I can always look at the key and find an associated node that matches that key in at least one digit, right? This is what that first level of routing table gives me. Now suppose I get a message with a key that already matches my own node ID in the first digit. So it has a 6, okay? So now I need to forward it to a node that has a 2-value prefix match, and I'll do that by looking at the second level of my routing table, which consists of nodes that all start with a 6 and have all the possible 15, 16 values of the second node ID, of the second digit of the node ID. Okay? So this enables me now to route a message on its second hop, and so on, right? Again, my own node ID is 6.5, so when I get a message with a key that starts with 6.5, I need to use this level of the routing table, and I can forward it on its third hop, and so forth. And you'll see that, so at some point, of course, as you keep playing this, depending on the size of the system, you'll get to a level where nodes with a particular match, no longer exist, because there's just not enough node. You've run out of nodes. And it's not hard to show that this will happen after approximately log base 16 of n levels, right? Which means the size of that routing table is asymptotically exactly that. And in addition to that, each node knows its immediate neighborhood. Okay. So again, this is my own node ID. That's me, my IP address, my node ID. This is my immediate neighbor in the clockwise range. This in the clockwise direction. This is my immediate neighbor in the counterclockwise direction. Okay? And that's important because when I'm receiving a message with a key that's very close to my own, I need to decide, am I responsible or is it my neighbor? Okay? Or my neighbor's neighbor. I need to know which way to go. That's all you need. Okay, how do we route? It's pretty straightforward. Let me just show you. I'm not going to plan to go through it in detail, but you basically, when you get a message, you just see, first of all, if the key is within the range of keys covered by my neighbor list. Okay, so is the key in my immediate neighborhood, then I can decide whether I am in fact responsible or whether I should push it to my left neighbor or my right neighbor. Well, sorry, I should say clockwise and counterclockwise because we have a circular space. If that's not the case, then I use the routing table and I basically compute how many digits the key is already sharing with my own node ID. Okay, and that'll determine which level of my routing table I want to look up, and I look it up with the next digit of the requested key, and then I'll forward the. Well, first of all, I look if that routing table entry exists, because it may not exist. Maybe there is no node in the system that has a longer prefix match. If it exists, then I forward the message there. Else, there is this case where this is actually a relatively rare case, which I won't go in, but in this case, you basically say, okay, the key is not close enough that I know which one of my neighbors is responsible for it, but no node exists that has a longer prefix match. So let me just see for the node that has the same length of prefix match, but is arithmetically closer to that key among all the nodes I know of, both my neighbors and all the nodes in my routing table. And one can actually show that this way of routing things is always loop-free, because what we're doing is we're always forwarding a message to a node that is closer to the key than our own node ID, which means it cannot possibly come back, right? So the routing is always loop-free. You always make progress. Okay, let me give you sort of a more visualized view of basically this routing table. Here you see it as sort of in a table depiction. If we look at the identifier space, it looks the following. Now I'm going to play a little trick on you now. Remember we talked so far about a routing procedure that always matches a hex digit in each hop, right? So 4 bits in each hop. Of course, how many bits you fix in each hop is just a configuration parameter. Okay. If you take less bits in each hop, you get an even smaller routing table, but you get a longer routing in expectation, more hops, more routing hops. Okay. In fact, what changes is basically the base of your logarithm. If I take more bits, I get shorter routing hops, shorter number of hops, but larger keys. So the little trick that I'm going to play on you now is that we're going to switch to octal, meaning, I'm writing now keys and node IDs in octal, so 3 bits per digit, digits ranging from 0 to 7, okay, which means that our routing tables are half as large. Our expected number of routing hops is a little longer. The reason I'm doing that is that it's easier for me to draw this picture. Okay, so I hope you're not confused by this. So in this view, my top-level routing table consists of something like this, where I have a pointer into each of those 8 segments of the key space. Okay, all corresponding to the leading digits from 1 of 0 to 7. And notice, by the way, that which neighbor I point to, which node I point to within a segment doesn't matter, right? All I need to have is I need to have some neighbor in this particular routing entry in this segment of the key space. I can pick and choose which one I use, because there's generally many of them. So in the second level of the routing table, what do? Well, here we need to divide the segment that we are ourselves in, so the 3, the segment with the leading digit 3, into, again, 8 subsegments, okay? And we want to have routing table entries that point into each one of them. And again, I don't care which node precisely I'm pointing to within that segment, as long as it has that particular prefix, okay? And of course, I can play this. In the next level of the routing table, I would subdivide this little segment here, again, into 8 different ones and have little pointers, but I'm not going to draw that, okay? Here's yet another view, if you want to sort of have an intuition of what this spatially looks like. So imagine the top level of the routing table. Again, we have this node that starts with the node ID 317 octal, and it has, at the first level of its routing table, pointers to the 7 other nodes, right, that have the other leading digits from 0 to 7. Okay, so that forms a cube, if you will, and you have a connection to each one of those. So not only the ones that are shown here, but you also have cross edges to this one, from here to here, and from here to 0. Okay, I didn't draw those to not confuse things too much. And in the second level of our routing table, we basically have this nested cube here with node IDs that start with a 3, and so on. Okay, this is the third level of the routing table. So you can, if you think about what the overlay looks like from the perspective of one node, you can imagine it as a set of nested cubes. Now, if we went back to hexadecimal notation and fixing a hex digit in each routing hop, then of course we would have at each level not connections to just 7 other neighbors, but to 15 other neighbors. So each of these cubes would turn into a 4-dimensional hypercube. Okay, and you see why I chose octal, because I didn't want to draw that. So you would get a set of 4-dimensional hypercubes, and if you go to even more digits, the hypercube increases in dimension. Now, one other thing to realize is this is just the view from one node, right? Because remember, the routing tables are not necessarily symmetric. Just because this node uses this node here as its routing table entry for leading digit 4 does not mean that this node points to this one as its top-level routing level entry for value 3. It can, it doesn't have to. Okay? So the view is not symmetric. The take-away point here is, well, actually, we'll have that on the next slide. So I've shown you one particular way of doing this key-based routing, right? There's actually many, many different ways of doing it. Lots of protocols have been proposed. I would argue that from at a high level of first approximation, they're pretty much all the same. You want to always construct an overlay that has a few long-range links that quickly get you into all the different portions of the key space, and then you want to have more links into closer and closer regions of the key space, right? That's going to give you the ability to, in the first hop, get to any key, wherever it may be, and then very quickly go finer and finer towards the particular location of the key that you're interested in. So basically what you're doing is you're constructing a complex network that has very low diameter, okay? Meaning the distance between any 2 nodes is very short. And you have the ability to deterministically route along that short path, okay? Using very little information. That's what you do. So of course, one way to look at this is, of course, there's many different types of complex networks that have this property of small diameter, small world, fast mixing, and so forth. And social networks, for instance, have this property. These networks have similar properties, but they're actually engineered, okay? And in particular, they're also engineered to be able to route along these shortest paths deterministically. Okay. Yes?
So, the reason why we moved to such an organization was, one, to reduce the space that is needed to store the table. The other was to reduce the update traffic in the system per event of churn.
Yes.
So, have we been able to achieve the second objective?
Yes. So this is a very, very good question you're asking. And of course, I owe you the answer. Okay. So first of all, let me just say, of course, superficially, you could say, because we dramatically reduced the number of entries in our routing table, okay, basically from n to log n. Okay, there's far fewer information that we need to maintain. Therefore, the updates that we have to handle, of that information are proportionally smaller. But of course, this is a very naive view, because what I haven't talked about it is how much does it cost me to maintain this complicated structure. Okay? And so I owe you the answer to show you that, in fact, it's possible to do that without having huge overhead. Okay? And this is part of what the cleverness of these algorithms, where the cleverness comes from. Okay, so so what I just shown you actually goes back to some work called Plaxton trees by Greg Plaxton back in '97. That was more theoretical work, meaning it was sort of an algorithm that didn't have all the aspects that would allow it an actual deployment in the internet. So what people have done, and there's several protocols that actually build on this particular basic idea, in particular pastry and tapestry. They have added various things to make it practical for an internet deployment. So in particular, they added neighbor lists. Don't worry about these things, we'll go through them. They actually added self-organization. Your question basically is, show me how you can self-organize such a complicated network, and show me how to do it with little overhead. Okay, that's what we'll have to talk about. There's something called proximity neighbor selection, which allows us to route efficiently, not only in terms of the number of hops, but also in terms of delay. There's some dynamic caching. We'll have to talk about consistent routing, because we haven't talked about consistency at all. And also secure routing, which is what happens when some of the nodes participating in your overlay are actually not functioning properly, and even behave arbitrarily. Okay. So first of all, I'll just mention that in passing, I already showed you that it's necessary for the correct routing to know your immediate neighbors. For many reasons, though, it's much better to actually have a direct list of more than just your immediate neighbors, but actually some set of neighbors on each side of the ring. Okay, that gives you a lot of robustness. And this also helps with fault detection. Somebody asked about fault detection. Basically, what you do is you keep track of your immediate neighbors by periodically sending them keep alive messages. Right? Are you still alive? Are you still alive? You can't do that for every node in the network. That would, cause huge overhead. But if everyone does it for their immediate neighbors, it's quite practical. We'll also have to have some anti-entropy protocol to make sure that these neighbor sets are eventually consistent, because they're all overlapping, right? And we need to make sure that everyone has at least an eventual agreement about what the ring looks like. And it turns out that these neighbor lists also are a good way of supporting local coordination, such as tuple replication. Right? We're going to replicate tuples along these lists of neighbors. Okay, so let me see where we roughly are. Okay, so let's work through the self-organization. So this addresses your point, right? How do we maintain the structure? So basically the problem is, how does each node initialize and maintain its routing table and its neighbor list? Because that the union of these routing table entries and neighbor lists basically determines the overlay structure. Okay. So think of this overlay as being constructed inductively. Okay. The base case is you just have one node. Yes? Sorry? The previous slide? Mm-hmm. The microphone is coming.
Here we are updating the routing table according to neighbors. So at the lowest level, one node is there. So is it possible to organize some bunch of machines as one network? And we are like doing administration over one network. And when the message is coming to one network, and so another message is going to another network. And so this kind of message passing has been possible in that case. Because here, for example, if one machine has, for example, query for node ID, and if it doesn't have, so it is looks to the nearest neighbors which might have. So in that case, for example, here multiple machines are querying each other. So here, rather than machines are querying each other, we are organizing some bunch of machines as one network. So one network, first query is going to one network, and one like machine is there, and if it doesn't have, so it gives the query to another network. So we can reduce the number of that message and probably the size of routing table also. So is that possible, like subnetting?
So I'm not quite sure I understand your question, but I think you're trying to introduce some kind of a hierarchy, right?
Yes,
Instead
sir,
of
yes.
having one
Yes, sir.
key space, you're trying to have a hierarchy of key
Yes.
spaces. So it turns out what you're suggesting, we can discuss this more offline, but what you're suggesting turns out not to really be a big advantage in terms of routing table size. But it's actually an interesting idea because it does help you with something else, namely if you like to have a system that has an administrative structure, right? So suppose it's a big federated system where different organizations are taking part. And those organizations, for various reasons, would like to have the property that if they're looking up a key within the organization. Say, Microsoft is part of such a system, but it has a substantial subnet, if you will, sub-overlay, and it'd like to have the property that if you look up a key that tends to be or that happens to be stored within the organization, you would like it to be looked up entirely within the organization and not go outside. Okay? So for that, one way to achieve that is in fact to have such a hierarchical structure with different rings. Okay? We'll touch on that a little bit later. Okay, so again, right, we need to control the overlay structure because the overlay structure needs to hold for the properties to hold that we can route in log n hops. And again, we'll do that inductively. So the base case is you just have one node. It has an empty routing table, and it is its own left and right neighbor. Okay, so just imagine a ring. It has only one node in it. Okay, and of course it's its own left and right neighbor, and it is responsible for the entire range of keys. Okay? That's a valid overlay. It's just a singleton network. And then the inductive step is that we either add a node or we remove a node because it has failed or departed. So let's look at the node join first. Okay, so let's assume a new node shows up, right, with this particular node ID that it has chosen by hashing its MAC address, for instance. And it would now like to join the overlay. So it would like to join the ring. Okay. Of course, by having chosen a node ID, we already know where it should go, like at this red spot in the key space. But for it to be actually, in earnest, join the overlay, it needs to have a routing table where it points to all the appropriate other nodes, and other nodes point to it. Right? Only then is it actually integrated. So how do we find that information? So the first step is that, as in all such overlay networks, in order to be able to join the network, you need to know some existing member of the network. Okay? This is sort of a bootstrap problem. You need to do that using some outside mechanism. Maybe you look up some addresses on a website. Maybe you actually know someone in a social network who sends you, who says, I operate a node like that. Go to this IP address and you can join. So this is in general going to be a node with an arbitrary other node ID, right? Because you are just finding any old node that will help you bootstrap into the overlay. So how do you get the appropriate routing table entries? And here's the neat trick. You just have this node that helps you join, do a KBR on your behalf with a join message, which just says, I'm a new node and I would like to join this overlay. And you direct this join message towards a key that coincides with your own new node ID. Okay? So a new node basically asks an existing member of the overlay to please route a join message towards the key that corresponds to its own new node ID. So this will be routed in the usual way towards the node that is currently responsible for the key D46A1C. Okay? Of course, there's no such node because it's not in part of the overlay yet. Okay? But see what's happening. The new node basically is looking for information that it can use to fill its routing table. So what does it need for its top-level routing table? Well, it needs nodes. It needs, first of all, for the top-level routing table, it simply needs nodes with all the possible leading digits of a node ID. Right? It can actually take that from any node, so it might as well take it from the bootstrap node. Okay? Now, the second level of the routing table is a little bit more tricky because you need 60 nodes that all start with a D, okay, coinciding with the first digit of the new node's node ID. But see, what's happening here is we're routing through a node that has exactly that. It has a leading digit D. So we'll take the routing table from there. We go on. Now we need, oh, there's a bug here. I'm sorry. Should go through D4 here. Now this node has exactly the right information for the third level of our routing table, okay, and so forth. And then we end up at this node that is currently responsible for the key for our own node ID interpreted as a key, which means that this node knows the neighborhood in which we will insert ourselves. Okay? So this node will, in fact, provide us with the neighborhood information. And then this node simply sends us back this information. We can fill our routing tables. And we will, in fact, do a handshake with our immediate neighbors here so that they know that I have now arrived and will insert us into their neighbor list. Okay? And see, this only took one message, log n messages, and another message, right? So this is the log n. So with log n forwarding hops, log n messages, we were able to join this overlay. So the other inductive step, of course, is that a node fails or departs, okay? And that also requires some repair. So there's two things that have to happen. First of all, the neighbor sets, if I fail, my neighbors need to realize this and they need to remove me from their neighbor list, okay? And in fact, readjust the keys and move around tuples accordingly. So for that purpose, the neighbors exchange, as I said before, regular keep alive messages. And when those don't come for a while, right, you have a timeout, and at some point they agree that this node has now departed, and they remove it from the neighbor list, and they reacquire tuples from the replicas. Yes? Can we have the, yeah?
So in this case, if the node which is joining is a neighbor itself, then you will not have this routing happening, right? So you always have to choose.
So you mean that you happen to know an introductory node that is your neighbor in the network?
Yes.
Okay. Yeah. So that would actually be a bad idea, right? Because
yeah.
that
So
give
you have to choose the farthest one always, right?
No. Hang on. Actually, so this node, remember, because it's sharing a very long prefix with your own node ID, you will have all the right information.
Okay.
Now, of course, this is not going to happen in practice, right? Because the chances of that happening are very, very low. That you would just happen to know, a node that is very near you in the key space. But nevertheless, it would still not be a problem. Okay, so there is this keep alive. There's this fault detection protocol based on keep alive messages, and that's actually integrated with the neighbor list stabilization. So basically, what happens is periodically I tell my neighbor, "Hi, I'm here. Are you still there? And by the way, this is my neighbor list." Okay, and so they swap neighbor lists. They see if they have some information that the other one doesn't have, and they merge them in the appropriate way. And when a node appears dead, at some point the neighbors decide this guy's gone, right? So let's remove him and rejoin and reintegrate our neighbor lists. And this is done relatively eagerly, right, at that level, because you want to know relatively quickly that a neighbor has failed. Because what happens, of course, while a neighbor has failed is that keys arriving that this node is responsible for will not get answered, okay? Because that node is not answering. So you want to be relatively proactive about this. And the way you repair a neighbor list in general, because of course it could happen that multiple nodes in the same neighborhood are failing, is that you rely on the other members of your neighbor list by requesting their neighbor lists, and so you can actually merge and mend the ring even if multiple consecutive nodes in the ID space should be failing at the same time. It turns out there are some complications, which I don't want to spend a lot of time on now, but just very briefly. In the internet, you often have situations where there are routing anomalies of the sort that, I can talk to Lorenzo. Lorenzo can talk to Robert, but for some reason, Robert and I cannot communicate. Okay? There's some routing problem. So if you have a very simple, naive neighbor list stabilization protocol, I would tell Lorenzo, hi, I'm Peter, right? Lorenzo would tell me, hi, I'm Lorenzo, and by the way, my neighbor is Robert. And then I say, oh, Robert, I don't know him. I'll try to contact him. But I cannot, right? So I will say, oh, Robert is dead. So I will tell Lorenzo, Robert is dead. But he comes back next time and says, hey, Robert is just fine. So this will never stabilize. In fact, this will, a simple stabilization protocol will simply oscillate, and that would be bad because, the keys will be unavailable. In fact, you'll have situations where if a node comes in through me, I will say, sorry, nobody here, responsible for that key. But if the message somehow goes directly through Lorenzo, he will happily forward it to Robert, and things will work. That's very bad. For that reason, actually, you need to do a little bit more. So, Lorenzo would not only tell me that Robert exists, but he would also tell me how to get to him, namely through Lorenzo. And so I would exchange keep alive messages with Robert through Lorenzo. Okay? And that would be good enough for me. I would say, I know he's there, I can communicate with him. Not directly, but never mind. Right? We would still stabilize, and we would still be able to route. Yes?
So at a high level, is the eventual goal of both the join and the failure algorithms to guarantee that once the network voices and there are no more joins and no more failures, then a single key is mapped to a single node management? Is that the goal?
So very good question. Actually, the goal I'm after right now is somewhat more modest. Okay, I'm just trying to repair the routing structure so that KBR still works, meaning, typically in log n messages, I can reach any key. The problem you're touching on is called routing consistency, meaning, at any given point in time, at most one node is responsible for a given key. And it turns out that's more complicated. We'll talk about that probably tomorrow. Yes?
I know you're going to talk about this later, but just to point out that now that you trust me to tell you that Robert is alive, I can tell you that also Krishna is here, and Rodrigo is here, and whoever is here, make you believe that there is an entire world that I am aware of that we don't know whether that is there or not.
Yes, absolutely.
Talk about that.
The whole discussion so far assumes that all the nodes, right. Right. Absolutely. I should have said that, right? The model that we're pursuing right now is that there are only crash failures, meaning a node is either up, alive, response, and then it acts according to the protocol, or it's crashed. Okay? We'll talk later, again, tomorrow, what happens when you relax that assumption. Yes?
In the present example, Lorenzo's failure for you will mean Robert's failure.
Can you say again? Yes, that's right. When Lorenzo fails, I would also lose contact with Robert. So what the condition actually is, we'll get to that a little bit later when we talk about routing consistency. The condition needs to hold. I need to be able to talk to Robert through some member of my neighbor list. Okay. In fact, that's the condition for someone to be a valid member of the overlay. Right? I need to be able to reach him or her or it through some member of my neighbor list. So if Lorenzo goes away, that's fine if there's someone else here who can still reach Robert that I can use. Okay, so I need to watch the time a little bit. So, okay, so we talked here about how to mend the neighbor list, okay, using this stabilization protocol, keep alives, and this additional complication that sometimes I may have to talk to one of my neighbors through someone else. Okay, so the upshot of that is I have a way of always eventually converging on what the neighbors are. Now, we also need to fix the routing table, but it turns out to be we can be a lot more lazy about this, and this is important because the routing table is much larger, and we don't want to constantly ping all those nodes to see if they're still there. That would create a huge amount of traffic. So what we do is, in fact, we do nothing in the common case. Okay. And when we have a reason to use a routing table entry because there's a message that we need to route, and we try to route it and it doesn't respond, we say, oh, too bad, right? This guy has departed sometime since I last used them. That's fine because there's huge amounts of redundancy in the routing table. Remember, if the guy who has a longer prefix match with my message is not there, I can still route to any other guy in my routing table who is arithmetically closer to the node than I am. Okay? That's all that's necessary for the routing to converge. Now, my expected number of hops will possibly increase a little bit, but that's fine, okay? And then, as I notice that my routing table entry is bad, I will in fact ask some other people at the same level of my routing table for their corresponding level of their routing table, and thereby recover information about live nodes, okay? Another thing that you can easily do is, when I run in that situation that, you know, a routing table entry that I wanted to use turns out to be dead, and so I have to use another routing table entry, which is not quite perfect, okay? So I forward the message there. This guy is actually going to say, hey, this is strange. Peter is sending me this message, right? But I don't have a longer prefix match. He should have sent it to this guy, which I have in my routing table. So he proactively actually sends me back the corresponding node. Okay? So this is a sort of a lazy way of repairing my routing table. So the thing to realize, of course, here is that fixing my routing table, I can be very relaxed about it because it only affects the performance. Okay? My routing table is very stale, meaning it has lots of entries in it that are actually dead. It just means I have to more often route to non-optimal guys, which is going to tend to increase the number of hops somewhat. But it doesn't affect correctness. You know, the node will still eventually arrive, the message will still eventually arrive at the correct node. Whereas neighbor list integrity is in fact necessary for correct routing, right? If I don't know who my neighbors are, I'm in trouble because I might in fact misassociate keys, and I might in fact run into a situation where a message is not at its destination, but I still don't know anyone who's closer. Okay? That's why I have to be much more careful fixing my neighbor list. Okay. Yes?
Talked about how you detect nearest neighborhood to keep alive. Now, notice that dead entry is part of it.
When you're trying to route to it.
So you get an error path propagated all the way back.
No, you're just trying to open a connection to it, right, using the IP address, and there's no response. So you're saying, oh, doesn't work. Okay, so now, so far we have exclusively talked about how to achieve a logarithmic number, a low or logarithmic number of routing hops, right, as a performance goal. Of course, you know, if you have many, many routing hops, it's clearly going to be bad for performance and latency. However, it turns out that this in practice is a little bit too single-minded, okay? Because even if I just take 2 routing hops, which seems great, right? It's only 1 hop more than the ideal. If that routing hop actually takes me across the world, that could be really bad in terms of delay. So in particular, you know, look at this example here, where, you know, some node up here on Pacific Northeast is trying to route towards a key that starts with an 8. Okay, so key starts with a leading digit 8, and it just happens though that the routing table it has, the routing table entry that has, is some node that starts with an A, but that node is in India. Okay, so the node goes to India, and then, you know, this guy is trying to fix the next digit of the key, which is the 9. So it turns out that this message comes back to California, and then it goes back. Then it turns, and you know, let's assume here that in fact this is the correct node, right? So there's no longer prefix match. So it's a very small ring, and this is actually the node responsible for the key. So in terms of number of routing hops, there's nothing wrong here, right? I reached the destination in 2 hops, great. But in terms of delay, this, you know, probably will cost me an RTT of 500, 600, 700 milliseconds, maybe less if I'm lucky. Whereas had I chosen in my routing table a different node that, in terms of the prefix match, is equivalent, you know, it also starts with an A, but it's somewhere here in Utah, I believe, I could have been much faster. Okay? Same number of hops, far fewer delay. So the upshot is we cannot really ignore the underlying physical network. Right? We cannot just pretend like in the overlay network all that matters is number of hops. Now, one interesting thing is you may remember that in choosing our routing table entries, we had, at least at the top levels of the routing table, a great deal of flexibility. Okay? Because all we need in this particular case is some node that starts with an 8. Well, there are many such nodes, right? So if there are ones that are close to me in the delay space, in the physical network, might as well choose those. So this is what proximity neighbor selection does. And again, this is something that you'll find in some shape or form in all the practical DHT protocols, because it's simply necessary for performance. Okay? So the assumptions are that you have some way of some scalar metric for proximity. Typically, RTT, round trip delay, would be a good such metric. And the assumption is that any node, given the IP address of any other node, can measure this metric. And of course, that's also true for round trip delay. You just do a ping. And then you maintain this additional invariant on your routing tables, which is that in addition to having all the appropriate entries with the appropriate prefix, you try to choose entries that minimize delay, subject to the prefix match constraint, okay? Which is exactly what we should have done in this example here. We should have chosen this node. Of course, again, you're going to ask me now, how much does it cost you to maintain that additional invariant? Right? That seems non-trivial. But again, our inductive construction of the overlay network and maintenance of the overlay network tremendously helps us here. It turns out, actually, the only thing that you have to do, sparing you the details, is to make sure that the bootstrap node that you use, right, remember the one from which you route the join message, is a node that is near you in the delay space. So this, of course, still is non-trivial, because now, previously I could choose any node in the overlay as a bootstrap node. Now I really ought to be finding a bootstrap node that is near me. And then it turns out if I pick the routing table entries from that near node, right, it'll also route the message subject to this additional invariant that I'm always trying to use a nearby node with the appropriate prefix. So the routing table information that I gather will also consist of nodes that are near me, or the nearest among the set of prefixes that I need. Okay? There still is the question, though, is how in the hell do I find a nearby node in the network? Because I may just not know. It turns out you can again leverage the existing overlay structure to help you. You start with any arbitrary bootstrap node, okay? And of course, this may be one that's far away. Okay? You may have a bootstrap node that's in the US, but you're here in Bangalore. What you do is you get that routing table from them, and then you start pinging all of its routing table entries, and you find the nearest among them. Now, because that guy, of course, also does proximity neighbor selection, all the nodes that you find in there will tend to be, at least at the top levels of the routing table, will tend to be in the US. But remember, as you go down in the routing tables, there are entries that have longer and longer prefix matches. Okay? And that eventually that node will have reached a point where there is no such node in the US anymore, right? Because there's only so few of them. So inevitably, even a node in the US will have at the bottom layers of its routing table some nodes with a very long prefix match, which it has chosen among just a very small set throughout the world. And there will be some that are on different continents. That's the one you use, and you pick that node's routing table, and you keep iterating. Okay? And that'll get you closer and closer to your own region. So that introduces some additional overhead, but you only pay that once before joining. Okay, so let's see. I'm looking actually for an appropriate point to take a. Well, let's finish this. In fact, I think maybe the next slide will also help a little bit clarify what I just said. So let's assume for a moment that the invariant holds. Okay. The question is, how good is it going to be? What's the quality of the routes that I'm going to achieve relative to delay? So what you see here is on the left side is the familiar picture where you see the node ID space, and you see some node routing a message towards this particular key here, okay, seeking longer and longer prefix matches in each hop. What I have on the right side here is sort of the equivalent sequence of routing hops in the delay space. Okay, and this is a somewhat naive depiction here because I'm mapping the delay space into a two-dimensional plane. Right? That's not actually something you can do. The delay space in the internet requires many more dimensions, and in fact, it's not even Euclidean. Okay, but for the purposes of this discussion, this is good enough. Okay? So, and what you see here is that in this picture, I'm sort of claiming that this first hop you're taking is very short in the delay space, okay? Meaning it has very low delay. And the next hop you see is larger, is longer by some multiplicative factor. And in fact, that keeps increasing on each hop, and the last hop is this giant hop right towards the destination. So giant hop means very long delay. Why did I draw this picture? Am I just making this up? So I'm claiming basically that, in general, in expectation, on any one of those overlay routing hops, even though the first hop takes you a long distance in the key space, it'll take you a very short, oh, I shouldn't do that, sorry. It only takes a very short hop in the delay space. And then I'm taking shorter and shorter steps in the key space and longer steps in the delay space. Any idea why I'm drawing this picture this way? Or any reason you can imagine why that should be true? Right. So that's right. So what this is implying is that the further I go down in the level of the routing table, in expectations, the routing table entries are going to be further and further away from me. Okay. But why might that be the case? Sorry? Exactly. That's exactly right. So again, the first level of my routing table, which is the one I use on the first hop, okay, is going to be just to some node that matches the key in one digit. Okay, so there's a lot of choice. Right? So if I'm picking a node with a D, 1/16 of the participating nodes are going to have a D in expectation. Okay, so there's many of them. In a large system, there's many of them, which means that if I'm doing a good job in picking nearby neighbors, I should be finding one very close. Okay, whereas the set from which I'm selecting, if for the second level of my routing table, the D4 in this case, there's only 1/256 of the population that has that prefix in expectation. So I'm selecting from a much smaller set. So if I'm assuming that these nodes are more or less sort of randomly placed around the globe, the expected distance should be larger by some multiplicative factor. Of course, it's not going to always be so pretty, right? And in particular, the absolute values, there's no absolute values here, right? The point I'm trying to make is that in the expectation, the delays you're seeing, we're gonna tend to multiplicatively increase with every successive hop. However, if that's the case, right, that's quite nice because you can see that even though in the early hops I might be going different places, right? I'm not going actually towards in the delay space. I'm not necessarily moving towards the destination. I'm going sort of randomly because I'm just selecting nodes with the longer prefix match. So I might be going the wrong direction, right? In this case, it doesn't matter that much because these initial hops don't actually, they're sort of, so to speak, in the noise compared to this last hop, which dominates the previous ones. And that's always by definition going to go to the right place. So this is actually, if I got to choose, how to distribute my latencies over the successive routing hops, this is what I want. It's just a happy coincidence. So one can analyze this, and one can actually show that in practice, with real internet deployments, the resulting average delay stretch, that is, the ratio of the total delay of an overlay KBR communication relative to the latency of a direct hop, one hop communication using IP is around 1.3 to 2.2. Right? So this is a fairly reasonable delay stretch. In fact, one can analytically derive this precise value, the expected delay stretch, if you have an all pairs delay distribution between the participating overlay nodes. So this is interesting, right? You can get you can control the delays. That is basically what this says to something at most, maybe a factor of 2 or a little bit more than what you would have in direct IP communication. And the second property that actually results from this PNS is called route convergence. And that says if you have nodes that are nearby in the delay space, okay, and they are routing to the same key, which the node responsible for that key may be far, far away, the routes towards that key will tend to converge early. Okay, so let's go back to this picture to sort of get an intuition. So if I had a node nearby here, let's say here, route towards the same key, I'm claiming that in expectation, that route would maybe take a hop here and then sort of converge early to that node and then follow the same path. Okay. Again, this is a result of the way you tend to optimize towards low delay nodes when you're filling your routing table, right? So, if there's a node in this range, at some point it's going to have to choose a routing table entry for D4 because D4 nodes are relatively sparse at this point. There's a high probability that you're going to be picking the same node. If not, it's very likely that in the next hop, when you're picking one with D4, 6, right, which are even more sparse, you would be picking the same node. You might ask, well, why is that interesting? We'll get back to that later. For now, let's just hold that thought, right? That once you do PNS, once you initialize your routing tables in a delay-sensitive way, the routes of nearby nodes, okay, towards the same key will tend to converge early. Okay, so let's see. Do people want to take a 5-minute break and maybe stretch legs a little bit, or should we go? We should go. All right, good. Okay. So so now that we've covered this basic material, let's go on to let's go back actually to this idea of maintaining shared state. Okay. Remember the idea was to have this hash table interface with a put and or an insert, if you will, insert value, key value, and a lookup operation or get operation. And now that we have this key-based routing primitive and we know how to partition the set of keys using consistent routing, we want to put these two together and basically implement a DHT. And again, many systems of that sort have been built and designed. That's pretty trivial at this point, right? I'm defining this interface, and so that every participating overlay node can invoke those operations. I'm going to decide which node stores a given tuple based on consistent hashing, and I'm going to simply turn both an insert and a lookup into a KBR, right, key-based routing, which will always forward the message to the node responsible for the key, and that node will implement the appropriate action, either insert the tuple or deliver the result. And the nice thing is this is completely decentralized, right? I did not need any centralized controller node. It's fairly scalable, right? We've seen that the routing table sizes only increase logarithmically with the number of nodes. That the number of hops you're taking increases logarithmically with the number of participating nodes, and that the actual delays should be reasonable. And of course, the more nodes you have, right, the larger the capacity of tuples you can store. And because lookups to different keys started from different nodes in the network do not have to go through common nodes, there are no obvious bottlenecks. Okay? At least not if you talk about a workload in which different nodes access different keys. Of course, if you had a situation where everybody would pound on one key, that would be a problem because there's only one node responsible for that tuple, and it'll have to, in fact, handle all of those requests, and that's something we'll have to worry about. Okay, so let's look at a little bit more at how we do replication. So the simplest way of doing that is to, and I mentioned it briefly before, to instead of storing a tuple only on the node whose node ID is closest to the key, you actually store it, say, on the 4 nodes closest to the key. Okay. So now you have replication factor 4. And the nice thing is that if the node fails, like this node that's currently responsible primarily fails, then a new node will go into range, like this one will come in here, so it will acquire a replica, but the other 3 nodes are still responsible, so they just hang on to the copies that they already have. Okay, so this works out quite nicely. When you have an insertion, okay, the message will go to the node currently responsible, so it's closest to the key, and it can forward the value to all the other replica holders. Keep in mind, right, at this point, we are not talking about consistency. Okay? This is something we'll handle later. Yes?
There is no relationship between closest neighbors and distance.
This is correct.
Right. And does that impact failures? And when you do a failure, the amount of readjustment
Yes.
you have to do. It's hard to imagine
Right. So,
how this works.
this is quite correct. So a result of this simple way of doing replication is, of course, that the nodes that hold a replica of an object will, in expectation, be widely distributed. Okay? Because remember, the sheer fact that those numbers have those nodes have similar node ID values says nothing about what relationship they have. In fact, it's quite unlikely that they will be part of the same organization or be based in the same location. Okay? So what does this mean? It means that my replicas are going to be widely distributed. This is both good and bad. It's good, possibly from in terms of failure correlation. Right? It's very unlikely that if you're worried about natural disasters or power failure or large-scale network failures, that all of these replicas would be affected. On the other hand, coordination among these replicas might involve long-range communication. In fact, every update, is going to have to be pushed to all the replicas, and if they're all in widely different parts of the world, right, a lot of network bandwidths and delay will be involved in that. Of course, you can do differently, right? And again, we'll talk later about this. If you want to have more control over the placement of replicas, you can still do that. You just need a level of indirection. Okay? Then the node closest to the key will itself have a table that says, well, the replicas are actually stored somewhere else. Okay, but with this simple replication scheme, things will still work. In fact, you have this interesting property that if you do a lookup, on its way towards the node responsible for the key, it's quite possible that the node goes through one of the other replica holders. Okay? And in fact, remember, if these replicas are widely distributed, which is what you expect in a worldwide system, it's quite possible that these different replica holders are on different continents. Okay? Now, because of proximity neighbor selection and the way that you sort of always eagerly route towards the longest prefix match closest to you, it's very likely that the first replica that you hit is actually the nearest one on your continent, which is, at least for a lookup, interesting, right? Because it minimizes the lookup delay. Again, I haven't said anything about consistency, right? So things are in practice not going to be that easy. Okay. So another thing you can do, and this addresses this concern that we just mentioned, which is that suppose you have a workload in which there are certain keys, certain tuples, that are hit upon by lots and lots of nodes. Right? They're very popular. Maybe they have a key value, configuration value that everybody needs to periodically read. So in this case, you have a problem because the throughput is limited by at most by the capacity of the different replica holders as far as lookups are concerned. And one thing you can do is, particularly if you have immutable tuples, meaning it's something that's inserted and then the value is never changed, but lots of people want to read it, you can do some simple forms of dynamic caching. The way this works is that as you do a lookup, okay, you route it towards the key. What you do is that as part of answering that lookup, you also push a replica of the object into a cache on the node along the route just before it was found. Okay, so in this case, the lookup proceeded to the node that holds that's responsible for the key. The value is delivered to the client, but it is also stored on the intermediate node just previous to the node that actually held the replica. Okay, this is just some speculative caching technique. That's right. So in general, you may shortcut and actually deliver the message directly to the using IP, in one hop directly back to the requester. But you can still, of course, as a side effect, push back this this value, right, to the node from which you received the request. No, but it simply remembers where it got the request from. Okay, so there was an IP connection on which you received the request, right? You handle the request and you say, by the way, here is the value, if you want it. Okay, there's a simple negotiation, of course, because then the caching node may also say, no, my cache is already full, go away. Okay, so what will happen, and again, it's interesting to look at what happens in the delay space. Remember, the effect of doing that is actually to store a copy of the object that's much closer in the delay space to the requesting node, okay, in expectation. Which means that if you later on have another request, which is somewhere completely different in the identifier space, but turns out to be actually not that far away in the delay space, okay, because of that route convergence property that I earlier mentioned, right, there is some expectation that the path might actually intercept this node here, right, so travel the same path that the other request traveled, and thereby, hit this cached nodes, in which case you can serve it from there. Again, we're assuming immutable tuples. We're not worried about consistency at that point. Okay? And of course, you can play that game again, right? So you can push at that point another cached copy even closer to the point from which you got the request. And so if you have hotspots, if lots of people in a given geographic area tend to hit on that same tuple, it will automatically sort of push cached copies towards them. Okay. Right. So at this point, we have about 15 minutes. Okay. So we've looked at basic key-based routing. We've looked at consistent hashing. We've looked at some of the basic optimizations you can do, and in fact that you have to make it efficient. Yes. In bottleneck in what sense? Yes. So I think what happens in practice is that, in fact, you're more worried about this becoming a bottleneck, right? Because everybody's going to hit on them. So imagine if it turns out that this tuple is very, very popular, right? It's being accessed from different parts of the world. The effect of this technique is that cached copies are going to be pushed automatically into the various regions from which most of the requests come, right? So as an effect of this, you'll both get more replicas that are closer to the clients, and you get more replicas in absolute numbers, which all contribute to the total throughput that you can sustain. Okay? So in fact, this is very much a technique that will avoid bottlenecks for very popular tuples, on the assumption, once again, that this is an immutable tuple and you're not too concerned about consistency issues. Yes? So again, the more popular a tuple is, right, the more such cached replicas you'll create as a side effect of this dynamic caching, and you push them closer and closer out to the clients. Okay? So this is exactly what you want to do to mitigate that load. The fact that this node appears in many routing tables, I'm not sure is relevant in this context.
I think the question is thinking more towards that, let's say there's only one node is being chosen by every
Okay.
being used to route to the lower levels again and again. So in some sense, it's a kind of bottleneck.
So
Hinting that is this a dynamic route reconfiguration based on loads to the intermediate routing path?
you could do that, and I think we're going to see some of that later on when we talk about group communication. But here, I don't think there is an issue, because remember, especially towards the high levels of the routing table, you have lots of choice. And because of the proximity neighbor selection, it's very unlikely that, well, it's actually close to impossible that nodes far away in the delay space would choose the same node as an entry at the top level routing table. So right, in some sense, right, as the further you get away from the node that holds your key, the more fan out you have, right? So if you consider all the KBR path from all the possible nodes towards the same key, it's going to be a very wide tree at the bottom, right? And then it's going to narrow, and then eventually converge on this one node that stores the key. But there's tremendous fan out as you go down the tree, okay? And this is what makes this very unlikely that you would have bottlenecks of that sort. You're worried about bottlenecks as you approach the key, which is why you're trying to do dynamic caching, right, to shed that load and push it further down into the tree. Yes?
All the routing goes is the same. Like, might be the case that if you route from any of the nodes, the second last hop is the same, because it's narrowing as we proceed across.
Yes.
So in that case, that last hop, which was actually holding the value of might become useless now, right? Because the second last one is actually answering all the queries because it already has the replica to up.
Well, so remember, yes, it's quite possible that for requests that are all coming from the same region in the delay space, that they would all share the same path on the last few hops before the key, okay? But that's fine. In fact, you want that for the caching to work well. But requests for that same key from very different portions of the delay space would typically approach this a different path and go directly to the root. Okay. Again, just view have a tree in mind. If you form all the different paths from all the nodes towards the same key, it's this tree that's very wide and bushy at the bottom. Okay. Yes. Can we use the mic?
I'm not too clear about your comment. You said that a particular key, if that's very popular, that would eventually come close to a client. I mean, after several. I mean, I'm not too clear. I mean, how would that be?
So let's walk through this again, right? Suppose, so again, this is the delay space. Suppose the tuple becomes very popular in this region of the delay space. Okay. So because those routes will tend to converge early, they will suppose they will tend to gather here and then take that joint path towards the root. Okay. Because as part of this dynamic caching, we are pushing back cached copies of the object. We are going to create more and more copies closer and closer to the area in the delay space where those clients are that are issuing the request.
Okay, so essentially the node where you need to create a copy is decided by the number of hits. That's
yes, in some sense, right? But remember, the simple rule is that if you get a request, you push it one hop back from where you found it.
Oh, okay. All right. Okay, so that automatically. Okay. Oh, yeah.
And of course, these are cached copies, which means they can also be evicted by other requests that are coming, right? So if it turns out that you replicate this thing down here, but then you don't get any more requests for that object.
Yeah, that would be evicted eventually. Yeah, right. Yeah. Okay.
Okay. All right. So yes.
Then only it propagates back.
So in this simple technique, every time you do that, you push back one, which means there's going to be the caching is fairly aggressive, right? And many things will be evicted quickly. What you're suggesting is perfectly reasonable, and I think if I were to implement this in practice, I would have a very close look at approaches like that. Okay, so again, we talked about how to maintain shared state in this distributed hash table using this key-based routing primitive and using consistent hashing. What I'd like to talk to you about next is that, in fact, it turns out that this underlying key-based routing primitive that we constructed to help us implement this distributed hash table is in itself useful for other types of applications that go far beyond just a DHT. Okay? So it turns out that these KBR can also be used very conveniently to dynamically construct group spanning trees. Okay? Very quickly, if you think, again, we've talked about a very similar subject just now. If you have a group of nodes route towards the same key, and to take the union of their path, that union of those paths will form a tree. Okay? That has as the root the node responsible for the key, and at the leaves the nodes that are requesting that key. Okay? And this spanning tree you can actually maintain and make persistent very trivially, just as a side effect of routing towards the key. And now you have a way of communicating in that group and implementing various things such as event notification. You can even do content distribution or things like publish, subscribe, right? Where nodes are subscribing to a particular topic and get a notification every time something is published relevant to that subject. You can use these spanning trees to aggregate values in a dynamic fashion. And you can do sort of various forms of application-specific caching. We just looked at the simple strategy just now. And it turns out people have actually used this capability also to implement things like anonymization networks based on onion routing or similar techniques. So let's look at the very basic idea. So suppose you want to form a group of nodes for whatever purpose. What you do is you just pick a group identifier, and you do it the same way you pick any old key. You choose some quantity that's unique to that group. You hash it. That is your key. Okay? And you interpret that key in this case as the group identifier. And then you have all the nodes that are interested in joining that group route towards that key. Okay? And the union of the KBR path towards the key is going to be the spanning tree of the group. And you simply persist that. So you make sure that all the intermediate nodes in the tree remember that with respect to this particular group, there are the children and this is the parent. And once you have that spanning tree, you can implement things, the conventional group communication primitives that are well known, such as multicast and anycast. And notice that if you do that, because joining a group just requires me to route towards the key, the expected cost of joining a group is just the cost of a KBR, which is log n messages. And the other nice thing is, if that group spanning tree, of course, is going to sometimes fail because intermediate nodes are departing the system or failing. Okay? So that tree is going to break at that point, but we can repair it very easily by just repeating our join message, again routing towards the key, and it'll be fixed. So let's quickly look at how this happens. Some people want to join a group. They pick a group ID, which happens to be associated with this node here. This is the group ID. And then, any old node that wants to join simply routes towards that key. And then, because this is a special group join message, okay, all the intermediate nodes will know that in addition to forwarding the message, they should also construct the tree, meaning they should remember something that under this particular group ID, there is now a child, which is exactly where the message came from. So as part of the this routing the message towards the group ID, you're actually forming a tree in reverse. In this case, this is a degenerate tree that only has one strand. But if other people are joining, they also route towards this same key. That route will converge at some point, and you see the tree emerging. Right now, the tree has a second branch here that we are remembering. We've got another node join, and now here we've got a spanning tree with a few members in it. Okay, that guy is joining as well. So now this is our spanning tree that represents the group with all the members at the leaves. Okay, and some members are also interior nodes. It just happened that way, right? This guy also wanted to join the group, but he also happened to be on the path of some other group members that joined, so he's also serving as an interior node. Okay? Now notice other nodes that are also in the spanning tree are not members. Okay? They just happen to be on the path. So they're being asked to serve as an intermediate node, but they actually have no interest of their own in this particular group. That's sort of implied in what we're doing here. This is one of those things again, right? You're leveraging the simplicity of key-based routing to construct that spanning tree. Part of what you have to pay for it is that in that spanning tree are going to be some non-members. And this is something we'll have to keep track of. Again, because of the route convergence property, same picture again that we saw in dynamic caching, you will have a tendency that these spanning trees that you are constructing will have the property in the delay space, right, that the hop towards the root is going to be a long delay hop, and the further you go down towards the members, the shorter delay hops you have, again, in expectation. Okay? And again, that's not necessarily a bad property. In any case, we'll just keep track of that, right? You know that the tendency is that the further you go up in the spanning tree towards the root, the longer delay hops you have. The further you go down in expectation, the shorter you have, the shorter hops you have. Okay, so now once we have the spanning tree, it's easy to define some primitives. There's a create group. Create group basically just tells the root, hey, there is this key. You're responsible for it, and this special key is actually a group key. To implement a join group, you just route a join message towards the root, and the intermediate nodes remember to add the source of the message to its list of children with respect to that particular group. A leaf does the reverse. You route towards the key, and you tell the intermediate nodes, I'm no longer interested, so remove me from your children list. And once you have the spanning tree, of course, a multicast can be implemented by simply sending the message, injecting the message into the tree, and doing a depth-first search, delivering it at every node that you encounter. Okay. You can also implement an anycast. I think I have a slide in case you're not familiar with anycast. That's a related primitive where you're sending a message not to all the members of the group, as you do in a multicast, but to any one of them. Okay. So notice again, managing the membership is more or less decentralized because I don't always have to go to the root to add a member or to remove a member. Right? It's just determined by how soon a join or leave message intercepts the spanning tree, and at that interior node, the membership is handled. So it's not like all membership events will have to go to the root, which would create a bottleneck, right? If you had a highly dynamic group. Quickly, anycast, in case you're not familiar, anycast basically sends a message to a group, to any member of that group, and in some versions of the anycast primitive, you can also specify a constraint that says, deliver it to the first node member that you encounter subject to this particular constraint, which might say, I want a node that has this particular information stored or is interested in this particular topic. And the way you implement this, again, you do a DFS on the group tree, and you deliver the message to the first node that you encounter that satisfies the constraint. And at this point, this locality property of the KBR trees becomes also interesting because suppose you start down here. Remember those, as long as you're near the leaves, the nodes tend to have short latency. So these subtrees tend to be in some region of the delay space. So as a result of that, a side effect is that the node you find subject to your constraint will tend to be near you. Okay? So you don't go unnecessarily far away to deliver the message. So if you're interested in finding a nearby node subject to some constraint, this will more or less automatically do it for you. Again, what this is good for is for situations where you have very highly dynamic membership, because group membership events are very cheap to implement. So it's good for many groups groups with many members and groups with highly dynamic membership, nodes coming and going all the time. It is not suitable for bulk content distribution for two reasons. First of all, as I mentioned before, the spanning trees that you're constructing include non-members, right? You don't want to bother these with bulk content that you're distributing. And secondly, remember the spanning tree consists of overlay edges, which we have in fact carefully chosen to be for low delay. Okay? So low delay links are not always the best links to use if you're interested in high bandwidth, which is what you would want if you want to do bulk content distribution. Okay? What you can do though is you can use these spanning trees to construct a separate overlay, which is optimized for things like bulk content distribution. And you can use this anycast primitive to find appropriate members, right, to construct a secondary overlay. So this is an idea that actually has been pursued where you have a system in which members are all as part of this KBR overlay. They form these group spanning trees. And when they then want to construct a data plane for the specific purpose of distributing some particular content, and that content requires bandwidth, you use anycast to find appropriate members, right? So you're looking for members that also are interested in this content, that have available bandwidth, and as a side effect of the way anycast works, you will tend to find, subject to these constraints, nodes that are not too far away from you. We're almost, yes, let me actually just take 2 more minutes and then we'll finish. So the thing I want to leave you here, and I think this is one of the important takeaway points that I'd like you to note, is that we're talking of this technology mostly as distributed hash tables. But in reality, distributed hash tables with this insert lookup interface are just one abstraction you can implement with these key-based routing overlays. Okay? You can do other things. For instance, you can do this kind of dynamic group coordination with it, which is quite useful in many different applications and has been used widely. And in general, you also, as an application, have access to this KBR primitive, which you can use for other purposes. Okay, so think of DHTs not necessarily as just systems that support a put and get or insert and lookup interface, but as something that's more richer. Okay, so I touched on this several times. We have left out many important things. We haven't talked at all about how you maintain state with strong consistency in a DHT. Okay. And in some sense, we've only talked about the easy stuff so far. We've also been focusing on crash failures, as Lorenzo has pointed out. And if you relax that assumption, which you have to in a peer-to-peer system where you have open membership, right, things get much more complicated. And we've also not really seriously looked at large-scale correlated failures yet. Where a massive number of nodes fail at the same time, and that can cause a lot of havoc in the system. So in the next part of this lecture tomorrow, we'll remove these assumptions and see what happens when we do that. So thanks very much for your attention. I'm sorry for going over time, 5 minutes, and let's have a break.